Hello and welcome back. In this tutorial you will study about properties of the first derivative of the function. What is the first derivative? Well, basically it's a slope of the function. And if the first derivative is positive, then the function is increasing, going up. If first derivative is negative, then the function is decreasing, going down. Let us do some examples. Let's say I wanted to investigate behavior of this function x squared. So we find derivative of this function, which is just 2x. And now we have to investigate when this derivative is positive and when this derivative is negative. So you can see for all x greater than 0, derivative will be positive. So it means that function have to increase for all x greater than 0. And for all x less than 0, derivative is negative. So it means that the function have to decrease for all x from negative infinity to 0. And look, if we think about the graph of this function, this is just a parabola. For all x greater than 0, function is increasing. And for all x less than 0, function is decreasing. So you see, by the property of the derivative, we can understand property of the function without graphing it. Now, this point where a function change from decreasing to increasing and from increasing to decreasing is called critical point. So critical point is a point at which derivative is equal to 0. So we differentiate function, make it equal to 0, and for all x which gives 0 to the function, to the derivative of the function, this will be the critical point. Let us do some examples. Let us find out the intervals where a function is increasing and decreasing for the following function. F at x is equal x cubed minus 3x squared minus 24x plus 32. So my first step would be to understand where my function exists, because if you remember, rational functions, for example, wouldn't exist everywhere. In our case, we have polynomial function, which exists in the whole real line, so it's no problem with this function. We can differentiate it. So first step, we figure out domain is the whole real line. Next step is to find derivative of this function. So we just use regular differentiation rule in order to investigate derivative. So derivative would be equal to 3x squared minus 6x minus 24. The next step is to find critical points. These are points at which derivative is equal to 0. In other words, we have to take our derivative, 3x squared minus 6x minus 24, make it equal to 0, and find all x for which this is true. And if you solve this quadratic equation using discriminant formula, for example, you can find that x1 would be equal to negative 2 and x2 is equal to 4. These are critical points. Only thing that we have to check that these points are in the domain of the function. So function actually exists at these points. In our case, yes, they're in the domain, so both of these points are critical points. The next step would be the following step. We take domain of the function, and we subdivide this domain by our critical points, minus 2 and 4. We obtain 3 subintervals. And on each subinterval, we have to investigate sign of the derivative. If derivative is negative, function will be increasing on the interval. If it's positive, function is decreasing on the interval. So let's start. we wanted to investigate derivatives of the functions. Pick any point on the first interval, negative infinity, negative 2. Let's say point negative 10. Plug it into the first derivative. So obviously, you can see that it will be positive. Derivative is positive. It means that function is increasing. Now, next subinterval, minus 2, 4. The easiest point to take is 0. If you plug in 0 into the first derivative, you can see it's negative. First derivative is negative, function is decreasing. And the last subinterval, 4, positive infinity. Again, pick any point, say 10, plug it into the derivative, first derivative, you can see that it's positive. Since first derivative is positive, function is increasing. So we can say that the function is increasing on the intervals negative infinity minus 2 and on the interval 4 positive infinity. And function is decreasing on the interval minus 2, 4. Let us do more examples. Let us consider function f of x equal x plus 2 divided by x minus 1. The first step is the domain of the function. In our case, we can see that we cannot divide by 0, and x minus 1 is equal to 0 when x is equal to 1. So x is not equal to 1 would be our domain. The next step is to find derivative. Using quotient rule, you can find that derivative would be equal negative 3 divided by x minus 1 squared. Now we wanted to find critical points. These are the points at which first derivative is 0. But look, in our case, minus 3 over x minus 1 squared, it's never will be equal to 0. We cannot find any x which we would plug in a denominator, and minus 3 over this denominator would give us 0. So what does it mean? We don't have any critical points. What does it mean? It means that through the whole domain, function will be either increasing or decreasing. So we still have to check it. So I take domain of the function, and we have to throw away point 1. So this point 1 will split our domain into 2 parts. And in each subinterval, we have to check the sign of the function. So we take first derivative, and we pick any point on each subinterval and plug it into the first derivative. Let's say we pick point 0. If you plug it into the first derivative, my denominator always positive because I'm squaring it, and my numerator is negative. So it means that it doesn't matter which interval we pick, the first derivative always will be negative. So since first derivative is negative, function is decreasing on both subintervals. So function is decreasing over its domain. Let us play with domain. You can see that domain, if we tweak domain a little bit, then the function will change. We can figure out maxima and minima points of the function by looking at the graph. If we consider function y equal x squared on this small subinterval from 0 to 2. So if I consider this function on this closed subinterval, we can see that the minimal value of this function is at 0, and maximum value is here at 2. Let me now twist a little bit this domain. So I consider the same function, the same part, but I will just take one point out of it. I skip this point. Basically, it's all points except the 0 point. Look what happened now. We don't have any minima point, because we're getting closer and closer and closer to point 0, but we never get into it. But we have one maxima point. So my interval, which I'm considering right now, it's from 0 to 2. 0 we exclude, and 2 we include. If I now consider the following interval, so I take the same parabola, and I take 2 points, which I exclude, 0 and 2. So I'm including any points in between, but 0 and 2. So I take basically open interval. Any points except 0 and 2. We don't have any maxima and minima for this function. That just does not exist. So you see, if we tweak a little bit domain, the whole picture changes. All maxima and minima are changing. If we consider the following picture, let's say this is the graph of the function f of x, we can see that this function has some peaks, right? And we can right away, we can say that, well, this is probably maxima, and this is minima point. But now we have also some understanding like general maxima and minima and local maxima and minima. What are these? So if we move from the left side to the right side, we can see that sometimes we have peaks, sometimes we have falls. So if we just consider our function on this subinterval, we can say that, well, we have peak in here, right? Here we have minimum, here we have again peak, we have again minima, and so on and so forth. What happened with those? Look, our function is increasing here, and then it starts to decrease. What happened here? Well, our first derivative on this subinterval was positive, so function is increasing. And on this subinterval, the first derivative is negative, function is decreasing. First derivative changed sign from positive to negative, and we have this peak here, maximum. Now what happened here? Function was decreasing, and then it started to increase. So first derivative had negative sign, and then in this subinterval, its function is increasing, so first derivative is positive. And we have minimum. Now again, first derivative will be negative because function decreasing. And here functions to start increasing. So first derivative is positive. And we have minimum point here. So as you see, when derivative change sign from positive to negative, we have maximum point for the function. When derivative change sign from negative to positive, we have minimum point of the function. So those points we'll call local maxima and local minima points. And now if you look at the whole picture, and you can see that maxima over all maxima, it's also called global maxima. And minimum of the all minimums, it's called global minimums. So in order to find global maxima and minima, we have to find all local ones, and then just compare and choose the biggest and the smallest for global maxima and global minima. Well, since we figured out how to find maxima and minima, let us go back to our example and find what is the maxima and minima at our function x cubed minus 3x squared minus 24x plus 32. We figure out that we have two critical points, minus 2 and 4, and that function was increasing on these subintervals and decreasing on this middle subinterval. So we can say that since derivative change in sign from positive to negative, function have maxima here, right? And it's very clear that function have to go up, and then it's going down, so it have this peak, this maxima. Our first derivative change in sign from negative to positive, so function going down and then going up. So it have to have some minima here. So we can say that we have global and local maxima and minima at the same time. So negative 2 will be global maxima, and 4 will be global minima. Let me now change the domain of this function just slightly. I will cut this function and consider it only on subinterval minus 1, 5. Let's see what happened. Well, when we differentiate our function, we basically thinking about this interval, open interval, -1 and 5. We cannot differentiate function at these endpoints. Derivative does not exist there. So it means that with our procedure with the first derivative, we can check maxima and minima only on the open points, on the open interval. And then points -1 and 5, we have to check separately for maxima and minima. So we found that derivative of this function is equal to 3x squared minus 6x minus 24. And we find critical points for this. One point was -2, and another point was 0.4. Now we have double check whether these points are inside of the interval. Look, point -2 is not inside of our domain. It means that we are not considering it as the critical point. So we have only one critical point, 0.4. Now we take our domain from -1 to 5, and we subdivide it as before by critical point, 0.4. And we check sign of the first derivative here. We've done it before. We find that in this middle interval, function is decreasing, and from 4 to 5, function will be increasing. So we have minima point here. But this is minima only for the inside points of this interval. Now separately, we have to check points -1 and 5. How do we do that? It's actually very easy. We have to take our values of the endpoints, -1 and 5, and critical point, and plugging in them into the original function. And then we will compare the values of this function and choose the biggest and the smallest. So we have to calculate f at -1, we have to calculate f at 4, and we have to calculate f at 5. So if you plug it in, you will obtain the following values. 52, f at 4 would be equal to -38, and f at 5 is equal to -48. And now we have to choose the biggest and the smallest one. As you see, the biggest value is 52, so this will be a global maxima point. The smallest one is 48. This is global minima. And -38, we figured out that it's minima, but it's not the global one, so it's local minima. Now it's your turn to practice.